Thank you very much, everyone, for inviting me, and thank you very much for your patience. Actually, we were quite a bit late. So let me start, and then we'll see. I'll take questions possibly after the presentation. So today I'm just going to talk about the role of statistics and applied statistics and how I have been using applied statistics in dealing with different topics in science. Being as an applied statistician, it's been quite a blessing for me because I was able to communicate with different scientists from different topics and different stories I've been able to hear. And so I learned a lot during this journey. And I'm going to take you through this journey from the beginning to very short, which is hopefully is going to be related to what you are doing and the need that you need in your research. You need statistics as well. So I will start with, hopefully it's not going to be a very long presentation, but I will just show you my collaborations in medicine, in sports science, in modeling ionosphere atmosphere data, and one of the parts that I'm very much proud is automated image analysis in art and art conservation, which again, image processing may not be only limited to art. It can be to the work that you are doing, for example, ultrasound images. You may be working with the spectral imaging in your topic as well. So these can be, again, useful for your case. And our recent activities on population scaling and resource allocations, and finally the invitation that join me in this journey as well, if you would like to make more changes in the world. So statistics in medicine. When I started my work as an applied statistician, I was in the University of Plymouth, Medical School of Medicine. I am currently an honorary fellow at School of Medicine. I was approached by one of the surgeons in that area, and he said that based on my observation, the patients who are presenting with acute appendicitis symptoms, they are not going to really suffer from the delay in surgery, because acute appendicitis means if you delay, normally this is a public common knowledge, if you delay the surgery, it's going to risk bursting in the body, or it's going to result in necrosis, it's going to result in infection. But his information and his observation, it showed that they are not really, in some cases, it doesn't result in complication after surgery. And what we did was that we used polynomial regression analysis to show that this his assumption and his hypothesis is a correct hypothesis. But what we found was that there is an age dependency. The patients at certain age, at the older age and younger age, they may suffer if you delay the surgery, but patients with middle age issues, they are not going to suffer from the delay in surgery. So what would be the implication? Because I don't know if how the medical system works in here. In the UK, we have NHS. So, and most of it is public funding. So that means you need to think about how long you are going to ask your patient to wait, how much is going to cost if you are going to schedule back-to-back surgeries. So that may result in some sort of rethinking about delaying surgery or not. With the same surgical group, we looked at the survival analysis. The surgeon that I'm collaborating with, Mr. Estelle, and he is expert in the pancreatic and liver areas. So what we did was that, again, another aspect is that a patient, when they come to hospital, either if they have cancer, if they have problems with the bile duct, with the gallbladder, all of these, and if they need surgery, the important thing is that for a surgeon, what factor they need to consider before they do the surgery, and how, if what do they need to do, what is going to tell them to carry on with the surgery before they open the patient, because sometimes if they are dealing with the cancer patients, they open the patient and they notice that it is not operable. And they identify inoperable cancer tumors compared to the operable tumors before they put the patient into the trouble of surgery. And if it is inoperable, how long the patients are going to survive, and if it is not operable, how long they are going to survive. So in here we use survival analysis. How many of you use survival analysis in your research? Have you heard of something to Cox regression model? Yes. Okay, so we used Cox regression model. Cox regression model is part of survival analysis. It tells you how long, it is known as the time to event problems. And it is telling you how long it takes for a certain event to happen. And the funny thing is that we talk about survival analysis, but in these cases, we normally look at the mortality. From the time zero that we start, how many patients are going to survive to the end of the observation, to the end of our monitoring process. So these are the, what I did was that I just put the name of our publications. You can always have access to my Google Scholar and look at these publications. So far we used polynomial regression analysis in order to identify whether appendicitis, they need to delay, they can delay surgeries for acute appendicitis. And also we looked at the survival models in order to identify patients, how long, how we can improve patient survival by looking at preoperative factors. But later on, we had another problem. Again, another model in statistics. Another question for you. How many of you have used logistic regression? Yeah, that's good. So can you tell me what sort of context did you use logistic regression?
So I did it with spatial regression analysis, but for child mortality.
Yeah, that sounds good. Again, can any of you tell me at what occasions we use normally logistic regression? What type of situation?
Yeah, check the influence of your risk factors to how it can impact your outcome. So like age and gender and like exposure.
Yeah. Okay, so that is correct. I'm not teaching actually. I know. So
scared to answer. Apologies.
No, the thing is that in statistics, and that is again, that is why I'm saying it is a blessing for me to see people from different topics. In statistics, for each type of variable, response variable that you have, we have a different methodology. For example, when we were looking at acute appendicitis, we were looking at a specific measurement of necrosis. So we had a continuous variable. Whereas in survival analysis, we are looking for a time period, how many patients are surviving. So we are looking at the curve. In the regression analysis, logistic regression analysis, you have a binary outcome. You have survived or not survived. You have where the medicine had an effect or the medicine did not have an effect. So you have binary responses in those sort of situations. And what we wanted to look at in logistic regression in the survival in the medical application was that whether before you do any surgery, can you predict the tumor is resectable or not? And how would you do that? Normally, they look at the X-rays and the margin of the tumor is clear. If the margin of tumor is clear, they say that this is operable, and for example, the survival of patient is higher. But sometimes the tumor has got lots of, for example, roots, and it may have expanded to other areas. And on those areas, they can say, okay, we do not do any operation of the patient because it's going to cause more complication. So was the tumor operable or not? So you have a binary outcome out of this. So that is why we looked at the what's it called, use logistic regression. And then obviously we were interested to look at if any socio-economic factor, for example, if you are at the higher in the UK, we have some sorts of hidden classes. We have the upper class, middle class, working class. So we are not going to acknowledge it, but those sort of classing exist. So if the patient belongs to the middle class or working class, does it mean that they are going to end up drinking more? And is it going to affect their liver or not? So that is what we wanted to look at, whether any class is going to affect that. And the way to do it, look at the postcode to see that to identify the classes in that study. And obviously, we had other factors to consider for the preoperative elements, such as radiological results, and also any other blood test. For example, if a patient is diabetic before, if their insulin is higher, if they have jaundice or not. Okay, so this is some of the applications of statistics in medicine. Now, I have extensive collaborations with the sports science as well. My sister, she's a sports scientist, and she used to be expert in gymnastics, so I helped her a little bit in her gymnastics analysis. But recently at NTU, I've been working with the sports science group, and their interest is in rugby. So again, we used logistic regression analysis in the outcome of the rugby, and some of them rugby matches. I think we found some interesting things that, for example, the idea was that if you play in the synthetic field, it is a synthetic grass field, you get less injured compared to the natural one, which it came out that it is a wrong assumption. And you are going to normally players are going to they have higher chance to get injured if they play in the synthetic field, which is the. And also our colleagues at a sports science group, they looked at how would the training load and the match load is going to affect the player's injury. And again, and the interesting thing was that if you make your player tired during the training, you are going to affect them further on later down the line in the match, and you will increase their chance for getting injury in the match. So it doesn't necessarily need to be in the match they get injured. It might be the effect of heavy load of training before the match is going to affect them. I am working with the sports group again on the Bayesian analysis of the growth rate for the football academy, and also how you can plan for the young athletes in the football academy to follow up their their professional development. But because that is still work under development, I can't really talk about it in much more detail. But we have established quite good collaborations with the sport science as well. So I'm going to switch the subject totally to totally different thing. Do you have any questions from logistic regression, polynomial regression, and survival analysis? Yeah.
In your surface and injuries, did you drill down to see what types of injuries were more?
I think we can get more details from the paper. They had an extensive big data set for the type of injuries, concussions because the main thing was concussion. But I can't recall whether the concussion was coming up at the top injury of the surface.
The artificial surface.
Yeah, artificial surface, yeah. But the same topic is again is in the Google Scholar. I think I haven't looked at it. Yeah, they had extensive data set and they haven't finished analyzing it yet because they are looking at some again because when you find out how much detail and investment they have done, they have GPS for the players when they are running around the ground. So they've got all this information collected and hopefully they are still having to use one for the survival. Any questions? Okay, so let's go to the totally different topic, physics. So back in 2013, 14, I was approached by my colleague in physics. And his work is related to the atmosphere and the satellite data. So what we have here is that this is Europe, and there is a satellite around North Pole, which I think it should be around here. It's called a storm satellite. It's collecting data. It's going around the Earth and collecting data. And what does it collect? It collects data of the ionosphere surface of the Earth. And what is it? They are coming from the sun. So they are going around the Earth and they stay around the Earth. But why are they important for us? All of you have got GPS, sat nav, everything. So when the sun is having some sort of a storm or any activities of the sun, it is affecting the movement of the ionosphere. At this level, at the F region, you may not see that much effect on us. But when it comes to these areas, it's going to affect the accuracy of our satellite data. It's going to affect our GPS data. So it is important for us to be able to model the data from the satellite data. These are just numbers. We get simply numbers. And we get, for example, in the day, in the morning, in dawn, in afternoon, at sunset, all of these data is changing. And as you can see, the F region gets thinner during at night. It is extremely important to be able to see what the behavior of data is, so that from the F region, we feed this data to the middle latitude, mid latitude, and low latitude, so that we can make sure that our devices are accurately working. So until the time that I meet my colleague, they were using a standard regression. And what does that mean? When you use a standard regression, you assume your data, the F region data, is following a normal distribution. How many of you have heard of Gaussian distribution or normal distribution, the bell-shaped distribution? Okay? So if you use the bell-shaped distribution, I'm going to use your white one. Can I use this one? So I will try to be as symmetric as possible. This is your normal distribution. Okay? So when you use the normal distribution in your modeling, you assume your data is distributed around the mean, around the center. So what does that mean in terms of the statistical calculation? That means you are assuming equal probabilities. So you have equal probability that you observed a specific observation on the right-hand side and on the left-hand side. Whereas when we looked at the data from the F region, so therefore this would have been an incorrect calculation in general, incorrect choice of distribution to use as a response variable. When my colleague approached me, when we looked at the distribution of data, the data looked like this shape. So we call it a skewed distribution, and normally a choice of distribution is a gamma distribution. So what does that mean? Again, that means your data is not symmetric. It means you have higher probability to get more observations in this area than this area. So when you model your observations incorrectly with these distributions or the normal distribution, you may end up with significant covariance in the model, but your calculation and your conclusion is going to be wrong. Whereas when you choose this distribution from the beginning, you ensure that you have assigned a correct distribution, therefore correct probabilities to your data. We use this under the generalized the GLMs, they have a wide choice of options, and one of them is gamma distribution. And the significance about this is that my colleague was extremely excited because this may sound a very simple statistical approach, but in the physics and in the area of satellite data, no one has done it before. So they were the first people that they introduced, or we were the first people to introduce generalized linear modeling for the satellite data and the swarm data. If you look online, we are the first people who actually started modeling this sort of swarm data. So that was one of our, what's it called, achievements. Any questions from this slide?
I was keen to see what your data set looks like.
It was a massive data set, and the complications we have is that it's changing. And the next stage for us is that to include the time varying parameters, because the same way that you see here, it goes like waves like these. So every time, and because the satellite is moving around the Earth, every time you see that this is moving like waves. It is very fascinating, but it's a massive data set. We get it as, I think, at every second, but you have to aggregate it, for example, to an hourly data set. And then it is actually depending on many other factors, such as the radiation we get from the sun, the information from the Earth, where the satellite is. So it is changing. Any questions? Okay. Now I've got something more exciting. So how did we use the statistics in art conservation and in art? Again, this is not a method limited to art. This is actually innovative method in art. They said imaging, this remote sensing imaging has been used for a long time for the Earth data. And imaging techniques, how many of you are dealing with imaging? Ultrasounds, MRIs? No one?
Not quantified.
Not quantified. And other people do it for us.
Yes. So, but again, this group at NTU, they are innovators in mobile imaging, remote sensing imaging. They design, I think over the time this has been developed, but they designed this device. It takes something called a spectral imaging. And what is a spectral imaging? we know that the natural light has got a bandwidth of 440 to 800 nanometer. That is the visible light, and then we have ultraviolet, and then we have what's it called? Infrared. Yeah. So if you put filter in front of your camera and take picture at each at each wavelength, you end up with something called a spectrum. So every material, every molecule of anything that we see around here, it's got their own fingerprint. So that means if you have coffee, it's got its own care. If you have egg yolk, it's got its own care. Everything. If you have copper, it's got its own care. For example, as far as I remember, one of these is the copper care. So the problem is that, can you see, this is a massive cave in this is a massive cave in China. It's called Tibet, China, Buddhist cave. So what they did was that the problem was that, can you see this square? So what they need to do is that they need to take pictures square by square, because they cannot obviously fix everything. And before you ask me about the size of data, we have thousands, 5,000, 6,000 images. So the problem they had was that they had these tens of thousands of images, and this is not only one cave. They've got lots of other pieces of art. So they were taking all these images, and what they were doing was that they were storing everything, and they didn't know what to do. So they were picking up this single pixel here, for example, and they were saying, oh, this is, for example, copper, or this is, but they couldn't analyze the entire surface of that cave. So what I got when I got involved, I designed a computational algorithm based on clustering methods, which is this is the result of our computational algorithm, that we managed to cluster a surface and identify what material they are built of. So what the biggest achievement we had was that we automated this clustering method. So that means automatically it analyzes these tens of thousands of images without a user gets involved, without they try to pick up one pixel and analyze them. So, and this resulted in us appearing in one of the most prestigious articles in the US, Archaeology, which we managed to analyze the entire of these caves using our technique. And also a publication in Nature from remote sensing and machine learning to the history of the Silk Road, and many other prestigious awards, which I will show you later in a bit. So to summarize, in terms of the statistical techniques, we use clustering method mixed with automated technique in order to enable a large size of the images analyzed and identified. And the technique was called multi-spectral imaging, which spectral imaging, you can have it in MRI, for example. You have a spectral imaging in MRI. You can even do a spectral imaging on a what's it called, on a certain surface of the body to find out, for example, what sort of material it is built. It's been used, spectral imaging has been used extensively in medicine, but in art is quite new. Okay, so the last part that we've been working on is called scaling models. Again, I'm a biologist. I suppose we have biologists here. No, not biologists. Have you heard of population scaling models? So population scaling models, it looks at the amount of wells, for example, these wells can be resources available for a certain population, and in relation to the area that they exist. The reason that are not, it's been used mainly in biology, but it is used in social studies as well for identifying certain indices of the population, how it is related to, for example, COVID-19 mortalities, for example, number of crimes in a region with respect to the population. And the nice thing about this sort of a scaling model is that you can consider the entire area of interest. For example, if you are looking at the country, you can consider the entire country and compare different cities and regions together. And as a result of that, we looked at the relationship between homicide, firearms, and offense, and domestic abuse reports arise from different processes with different levels of statistical incompleteness. And what was this? Because one of the things that we found out that if the crime is reported in a specific region, those criminals, they are not coming from that region. They are actually coming from a different rural area, for example, and or different city, a neighborhood city, and they commit the crime in a different, in a totally different city. And my PhD student, he worked on 2 different papers using the population scaling models. And what we included was that it was the spread of the data. What does the spread mean? Is that in all of these modelings that we are considering, we assume that this is the spread which you may have come across as the name of variance, the standard deviation. We assume the spread of the data is constant from one observation to another observation, but in real life, one observation can have a spread of this and another one can have a spread of this. So this is going to make your calculation more complex. And that is why we included modeling the spread and variance as well in this calculation. Okay. Any questions? So there's just a last few slides that our success stories in applied statistics is that our image processing algorithm is resulted in analyzing large data sets at the NTU that we had, which was accumulated over the past 20 years. And in 2021, we won the Queen's Anniversary Award before Queen passes away. So this award is the highest national honor award in the UK, and we are still working on it to make it more available. We've got the software out of this package, out of this algorithm that we have written. Currently, I am honorary fellow at the School of Medicine, University of Plymouth. I co-supervise MD students with them as well. And this is the SWARM project that we got funding from for the SWARM project to analyze the data from the SWARM satellite. And finally, again, based on these algorithms, we managed to get AI for DigiLab funding for cultural heritage. And the nice thing is that, again, this algorithm is not limited to art data. You can feed in any information, any data set, any imaging data set to it. I've been developing lots of collaborations. It's not only these universities. These universities, they've been involved with me in my recent proposal that you have submitted across the world, actually. I've got collaborators from Brazil. I've got collaborators from South Africa. This is related to the recent project that we have submitted and we are waiting to hear the results. And also from Turkey, from Egypt, and from Indonesia, and of course, UK as well. And some projects that I have recently submitted and we are still waiting to hear. We've got empowering. This project is looking at agroforest farming and how it is affected by the climate change and how we can come up with the approaches that it not reverse the effect of climate change, at least it reduces the effect of climate change. This is the project that myself I'm leading, which we are still waiting to hear from that. We want to see the effect of climate change on women's health. And from that, we've got 1828, which is the NGO company, NGO, that they work with the young, what's it called, young women and education. So, and finally, we've got the we've got the African research leaders just submitted it a few days ago. So let me see if I've got anything else. One of the main reasons that I came to UK, well, the main reason, of course, is to see all of you, but one of the reasons is that in the UK, we've got lots of funding calls that they encourage to work with different countries, and South Africa is one of the focuses in the UK. And I am looking into two different funding calls. One is the Wellcome Trust, and another one Apply Global Health. And I put the details on it that if any of you want to join me on these proposals, I'll be more than happy to talk to you and see how we can work globally. Especially this one, it's got a larger funding and larger time frame that it will be good to include as many as collaborators as we can.